I don't forget. Okay, so slide 24, changing gears. So extending our logistic regression and probit regression models to be able to address ordinal and nominal outcomes. That's what we're doing. Are we ready for this? Yeah, so these are very, very common. And I will point out, so the podcast Quantitude had an episode recently. I haven't had a chance to listen to it yet, where they were talking about logistic regression, and they titled their episode "Too Legit to Quit." No, this has been my joke for at least a decade. I can point you to slides from 2011 where I made this joke. This is my joke. So this is not me capitalizing on that. That has been my joke. And further, I have had a link to the Too Legit to Quit video, which is, this is the joke here. There's a hand signal for those of you who were not alive in the 90s. Too legit to quit. That it was a whole like dance. It's MC Hammer, and it was a whole thing. The video is like 15 minutes long, and the end of it is like a who's who of everyone who was famous in like 1991. So it's kind of fun to go back and be like, hey, I remember that person. I remember that person. So it's fun. I highly recommend. But too legit to quit is my joke. So everything that you need to be able to predict ordinal outcomes or nominal outcomes, you already know. There's nothing new to see here, folks. All that we're going to do is trick the model into redefining what we mean by 0 and what we mean by 1. It's exactly the same other than that. So we have a little bit of new terminology here. The way that I'm going to describe these models is that they operate through the use of multiple sub-models. So there's more than one equation that is being solved for simultaneously in these models. And so my term for that is submodel. I don't think that's a real word that people use, but it's the word that I use because that's what makes sense to me. So there's more than one equation happening at the same time to predict just one outcome, because we're going to carve the outcome up into multiple pieces. So in terms of terminology, if you have a categorical outcome that is definitely ordered, so a Likert scale, strongly agree, strongly disagree, neutral, like those sorts of answers, or how frequently do you do this, never, seldom, sometimes, always, those sorts of answers where nobody is going to disagree with you about the ordering of those. Those are going to be fitted into what is known as a cumulative logit or cumulative probit model. So the key word here is cumulative. That's for ordinal items. There's another one that can be used for ordinal items that is not used hardly ever. It's hard to find in software, but I actually like it way better. So if I had my way and I ran the world, I would do it that way instead, but I don't run the world. It's adjacent category logit. And this one, by the way, corresponds to partial credit models in the world of IRT. The first one, the cumulative model, corresponds to graded response models in IRT. And categorical outcomes, that word is polytomous responses in IRT. They have to have all their own words for everything. And then the last one here is categorical outcomes that are definitely not ordered. So nominal. What's your favorite kind of ice cream? If you're reading a story, which of these would you respond in terms of like a vignette, and what's the right response, or which one would you pick? Things where there's no ordering to the answers, but we still want to be able to predict which one someone is likely to choose as a function of predictors. This one has a bunch of names. I call it nominal. It's nominal in the world of IRT. It's also called multinomial regression, which is a bad name because all of these use the same multinomial distribution. You can look it up as a generalized logit link or also a baseline category logit link. All of those words are going to describe the same type of model, but it just boils down to whether or not you're assuming that the categories are ordered, you're not sure, you're willing to say that some of them are, but you're not sure, or no way are they ordered, are the three sort of families that we'll talk about here. Okay, with me so far? And I'm not even out of time yet. It's only 1:26. I got to keep looking at the clock. All right, so the first one. We're going to spend the most time on this one because this is very common. And it is known as a cumulative model, as I said. Another term that you will hear this model described as is proportional odds. So that terminology is specific to this type of model. It's a graded response model in the world of IRT. And here are the ways in which you can ask for it in the different software packages that I will be demonstrating. The key idea is that for each of C categories, we fit C-1 submodels simultaneously that each divide up the possible answers into two groups. So if I have 4 options and the options are labeled 0, 1, 2, 3. So these are not really numbers. The numbers are just labels at this point. So this would be like strongly disagree, disagree, agree, strongly agree, something like that. Then because I have 4 choices as to what the categorical response could be, I need 3 submodels. If I had 5 options, I'd need 4 submodels. And each one is going to use all of the answer categories. So the first submodel is going to predict the logit, we'll say. It can be the probit too, but we'll just stay in logits for now. It's going to predict the logit of either a 0 versus or not 0. So 0 versus 1, 2, or 3 combined. So it's a binary submodel. 0 or not 0 are the 2 choices. The second submodel combines 0 and 1 as one possibility, and then combines 2 or 3 as the other. And then the last one combines 0, 1, and 2 as one possibility versus 3 as the other. So each of these is binary. And the part that is in red is like the 0. I'm putting air quotes in for those of you who are listening from elsewhere. Air quotes around 0 is the red, and the green is the 1. So the second part, if you're red-green colorblind, I apologize. It's the part before the versus after is what I'm going with. The part before is the 0, the part after is the 1. And so across the 3 models, you end up predicting the probability of a 0, a 1, a 2, or a 3. But it happens in this sort of convoluted way. So these are known as indirect models because of the convolution. And one of the challenges in fitting these models is figuring out if the model is predicting the 0 or the 1. So if your model is predicting the green part, then it's written with intercepts and slopes. If it's predicting the red part, it's written in thresholds and slopes. So here is an example empty model with no predictors at the bottom here. So submodel 1, the way that I would write this, is the logit that corresponds to the probability of y greater than 0. So this is written that I'm predicting the logit of having answered 1, 2, or 3 combined, is an intercept. So that beta 01 is my way of saying this is beta 0. That's what the first subscript is referring to, and the second subscript is referring to which submodel beta 0 is for. So the probability of y greater than 0 is given by e to the model over 1 plus e to the model, same as usual. The probability that y is greater than 1, so that y is 2 or 3 combined, and then the probability that y is 3. Okay, with me so far? So up to this point, we've only had 2 answer choices. We only needed 1 model. If I have 3 answer choices, I need 2 submodels. If I have 4 answer choices, I need 3. So it grows as a function of complexity of the response possibilities. And so then eventually, you can work backwards to figure out what the probability of each response is by going between submodels. So if I look at the first submodel here, it tells me 0 versus 1, 2, 3. Well, if I want to know what the probability of a 0 is, and my model is predicting the 1, 2, or 3, then I know it's 1 minus that to get to what 0 is. Okay, so that one is relatively straightforward. To get to the 1, then I need to take the predicted probability of a 1, 2, or 3 and subtract from it the probability of a 2 or 3. And that gets me to the unique prediction of just 1. Likewise, if I want to know what the probability of a 2, I start with the predicted probability of a 2 or a 3, and I subtract the predicted probability of a 3, and that leaves me with 2. And then the probability of a 3 is directly given by the last submodel, so I don't have to do any subtraction there. So this gets a little bit tricky to figure out the probabilities if you're doing it by hand, but good news, your software will take care of this for you. So you can ask for the predicted logits, and then you can ask for it to convert those predictions directly into the probability of each category. So at the end of the day, for each possible value of your linear predictor, you will have a distinct set of probabilities of a 0, a 1, a 2, and a 3 from this model. Okay, how are we doing? What's next? Oh, next is why I don't like this model. I don't. I'll just put it out there. So, caveat up top here. I don't know why I have the pink hourglass of death. Caveat up top here. Everything that we talked about with respect to link functions and asymmetry holds for these models. So most of the time you will see a cumulative logit or a cumulative probit. Those are symmetric link functions, but you can have a cumulative complementary log if you have skewed data. Those are harder to find, but they do exist. Here's why I don't like this model. Because on the surface, you're like, yeah, you can't just pretend that your 1 to 5 scale is real numbers and fit a line to that. That's crazy. We have to treat it as the categorical variable it really is. Well, how are we going to do that? We're just going to pretend that all the slopes are the same across submodels, so it goes right back to where we were before. So the default version of this model is the proportional odds model. You get a separate either intercept or threshold for each of the submodels, but then it forces the effect of your predictors to all be the same after that. In other words, even though we've set up these models to predict the probability of 0 versus 1, 2, 3, and then 0, 1 versus 2, 3, and 0, 1, 2 versus 3, we're going to say that the effect of 1 unit increase in x is the same, regardless of which submodel we're doing the prediction in. That bothers me. Like, we're making a big deal out of the fact that we have these 3 different submodels, and then we're going to put all the same parameters in all 3. So I'm going to show you how to not do that. That just bothers me. And yes, this is true in graded response models as well, because each item gets a separate A slope parameter, but across the submodels within an item, the A's are the same. So it is exactly the same limitation in both. So I'm going to show you how to fit what is known as either non-proportional odds or partial proportional odds, in which we can actually test whether or not the slopes need to differ across the submodels. So is the effect of x different if you're talking about predicting a y greater than 0 than if you're talking about predicting a y greater than 2? That's an empirical question that we can answer. It just takes a little more work to find those variants. Okay. This is the multinomial distribution. It is a generalization of Bernoulli. So Bernoulli has 2 possibilities. Multinomial has however many possibilities you need, but it works the same way. There is a separate probability for all but 1, because the 1 is determined since the probabilities have to sum to 1 as the parameters. So there's no variance. So it's the same story in the fact that we can't get this wrong. the multinomial has a separate probability for C minus 1 for possible responses. And the ordinal models, the nominal models, and the maybe ordered models all use the same distribution. So here are the other two that we will see. I'll have an example of the last one, but I don't have an example of the first. So the way that the other two models differ from ordinal is by how they carve up their submodels. So cumulative logit does the 0 versus 1, 2, 3, 0, 1 versus 2, 3, 0, 1, 2 versus 3. The adjacent category logit version, which is appropriate if you're not sure if your categories are fully ordered, it's called partial credit in IRT. It carves up like this. This is the one that I like the best because this makes the most sense to me. So in the adjacent category, you end up with conditional probabilities. So it's like, given that somebody picked 0 or 1, what is the logit that they picked a 1 instead of 0? Given that they picked 1 or 2, let's predict the logit that they picked 2 instead of 1. Given that they picked 2 or 3. So there's no requirement that like 1 has to be lower than 3. They carve up the response categories into sort of sequential adjacent submodels, which I think is a lot more directly intuitive and understandable, but for whatever reason, no one uses this. And then the last alternative is for nominal. So for unordered categories, it is essentially the analog on the outcome side of dummy coding your predictors. That's what nominal is. You pick one of your response categories as the reference, so like 0 for instance, and then each of your submodels gives you the predicted probability of the other category relative to the reference. So it's the same conditional setup. Given that someone picked 0 or 1, how do I predict the logit that they said 1 instead of 0? Given that they picked 0 or 2, I want to predict them saying 2 instead of 0. Given that they picked 0 or 3, I want to predict 3 instead of 0. There's another parameterization of the nominal model that's used in IRT, which is crazy. I've never seen that used in the context of regression, so I'm not going to do it for this class. The other version is where everything has to sum to 0, so there's positives and negatives, and I can give you a paper on it if you care, but this is the one that I think is a lot more intuitive. And so for this latter one, you can go between the models to figure out like the ones that are not provided, like 2 versus 3 is not given directly, but you can subtract like 0 versus 3 and then from 0 versus 2, and you can get to the difference. So either way, all of these models give you a predicted probability of each response eventually. It's just that they differ in the link, how they carve up the submodels. Yeah, cool. I made it. Let me go back. I didn't want to go there yet. So, let me go back to ordinal for a second. How are we doing? A few thumbs, a few nods. So within a submodel, we're right back to binary. So you already know how to do this. So do you remember when I said the hard part of this class is going to be figuring out what the hell y is? This is where we were going. That's why I said that. Because in addition to, okay, is it predicting the 0 or the 1? Now you have to keep track of what is being predicted in each submodel and how to interpret the slope as a consequence of that. So that's where it gets very tricky. And I would highly recommend, as I'm going to show in my example, starting with an empty model. Because the empty model is going to tell you how the program is carving up your categorical outcome into submodels and whether it's predicting the up or the down, the red or the green.
So, which logic model would you use for Likert data?
This one.
That's
This is what everybody uses. The problem with, let me see if I can get, the problem with adjacent category. Come on, you can do it. It's getting there. So adjacent category, I like better. Here it is. This is adjacent category because it's intuitive. It's this one versus that one versus this one versus that one. However, what if only 3 people pick 0? What are you going to do with that? So the adjacent category cannot borrow information from the other possible choices within each of the submodels. It only uses the responses to those 2 possibilities. So this can be harder to fit if you don't have a lot of responses in each of the categories. Whereas in the ordinal model that's cumulative, let me go back one more slide. Come on, you can do it. Every answer gets used in every submodel. All the data is used for every submodel. So it's less of an issue if there's sparse data in any one category because the other categories are going to get lumped in with it to help keep the estimation a little more stable. So I think that is why the adjacent category isn't as common, even though to me it seems way more useful. The other thing I forgot to mention, so for those of you who are Templin's advisees, he and I were talking about logits and probits, and he got into R and used the solver function to figure out the 1.701. He actually did it analytically. Yeah, I was just going to trust the people who figured this out that it's right, but he had to go and reverse engineer it, so he can show you how he did that if you're interested. But what he also told me about logits versus probits is that when you get into Bayesian estimation, probit is easier. Probit in Bayesian estimation allows you to sample directly from the posterior, meaning Gibbs sampling as opposed to any kind of rejection sampling, whereas logits, there's extra steps involved that make it a more difficult problem. So probits came first before logits. Logits are easier to work with in the sense of giving you odds ratios and predicted probabilities more directly, but they are more challenging to work with in a Bayesian setting. So that is potentially why we end up with more probit ogive stuff still, even though it's more of a pain to work with. So just as an aside on that. All right, 1:44. That means I need to shut up now. Any questions before we call it a day?
really quick. When we talked about testing for integers, or we talked about this in the beginning. Does that have to be the case for ordinal data? That it has to be equal integers?
So if you're fitting these models, you are not assuming that they're interval. You're assuming that it's ordinal. That's it.
But yeah, that's what I meant to say.
Yeah. So, and you're not assuming that it's normally distributed either. You're assuming that it's categorical. So you can't be wrong in these models. It's a nonlinear prediction of the predictors in the same way that the binary case was. All right. Anything else? All right. It was garbage day this morning, which means I say see you Thursday. Let me know if you need anything. Homework's due next week. So office hours later today if anyone wants to see me. Okay. Bye. See you then.